Hello, everyone, and welcome back. In today's episode, we are going to be learning about how to solve another particular variety of differential equation, a specific variety of differential equation called separable. So, what is a separable differential equation? Once again, a separable differential equation is one that can be expressed in a specific format. A differential equation is called separable if it is possible to rewrite the equation so that it looks like the following. Some function of only your output variable, some function of only y, times y prime is equal to some function of only x. Now, the first piece of this expression that's really important is that what is happening here on the left side is a product. A product of this expression here, which contains no x's, with the derivative of the function y prime, equals some expression on the right side that contains no y's. If you can rewrite your equation in this format, something that contains no x's times y prime equals something that contains no y's, that equation is given the special descriptor. It is called separable. So let's get some practice using this definition to decide if a couple of given differential equations are separable or not. So here's our first example. Y prime is equal to x times y. Is this differential equation separable? To answer that question, I'm going to try to separate the y's from the x's, and I'm going to try and separate the y's from the x's in a way that a function of only y ends up multiplied by y prime on the left side. To that end, I'm going to go in here and I am going to divide by y both sides of the equation. In other words, I'm going to multiply both sides of the equation by 1 over y. And so from that, I get 1 over y times y prime equals x. And this is of the absolute perfect format for something that's separable. On the left-hand side, I have a function of only y times y prime is equal to a function containing only x's. So this would be separable, yes indeed. Let's consider the next example. Is the equation y prime equals x plus y separable? In this case, I think the answer is no, because although it is possible to separate the y's and the x's, to do something like negative y plus y prime is equal to x, even though it's possible to separate the y's and the x's, we did not separate them in quite the correct way. The function of y on the left-hand side needs to be multiplied by y prime, but in this particular example, it's only possible to have them added together. So because they were not separated in the correct way, where I have a product on the left side, because of that, this is not separable. Okay, what about this example here? Y prime is equal to 3y minus 2. This is a pretty unique example because there actually is no input variable in this equation at all, right? It's only y's here and constants. And in a situation like this, we can separate the equation in a fairly extreme way. I can just divide this entire right side over to the left side, giving me 3y plus 2 times y prime on the left. and leaving the constant function 1 here on the right side. So I have the product on the left side that I need, the product of a function of only y times y prime. And what's left behind on the right side is 1. And 1 slash any constant function works perfectly well as the g of x in the format constant function OK for g of x. The most important thing is that this equation on the right side contains no y's. So in this particular case, I would say, once again, this is separable. This would be a separable equation because I was able to separate a function of y from a function of x alone in such a way that I had a product on the left side of the equation. Even though it was just a constant function left on the right side, it is totally okay to have a constant function for g of x on the right side. What about this equation here? I have y prime equals e to the x minus y. Let's think, is that separable? Well, if I'm going to work on separating the x's and the y's, the first thing that I'm going to do is use the exponent properties to separate this into two different exponentials, e to the x times e to the y. And now that I've done that, I can divide both sides by e to the y and rewrite this as e to the negative y times y prime equals e to the x. And I have rewritten this in exactly the correct format, e to the minus y, function of y only, multiplied by y prime is equal to a function of x only. It's separable. And then for a final example, let's determine if this differential equation is separable or not. We have y prime plus x times y equals 2 times x. Now that plus sign might make us a little bit nervous because the plus sign in exercise B created trouble for us. But I think in this case, we might be able to do a little bit of factoring. If I push that xy term over to the right side to isolate y prime, then I see that both of the terms contain an x which can be factored out. And if I factor out that x, and I divide both sides of the equation by 2 minus y, then in this situation, I get 1 over 2 minus y times y prime is equal to x. And this is of exactly the correct format for a separable differential equation. Okay, so this is how we determine if a differential equation is separable or not. We check to see if the equation can be algebraically rewritten into a format like this one. Function of only y times y prime is equal to a function of only x. Now that we have learned how to recognize separable equations, let's talk about how we solve separable equations. And to demonstrate the step-by-step process, I am going to use this final separable differential equation from the previous exercise. I'm going to walk you through the process of solving y prime plus xy is equal to 2 times x. Let us find the functions that satisfy this equation. So step number 1 of the process is, if you haven't done already, rewrite the equation in the standard format of f of y times y prime equals g of x. You have to do this anyway if you're checking to see if the equation is even separable in the first place. So if your equation is not in that format already, just go ahead and put it in that format. So we did that work upstairs in this particular example. I will steal this work and I will bring it down here. In the demonstration, this would be of the format 1 over 2 minus y times y prime is equal to, what was it? I forgot. X. Okay. Now that I've rewritten this equation in the sort of standard format for a separable differential equation, the next thing that I'm going to do is I'm going to integrate both sides of this equation with respect to x. We remember that when we are working with equations, you have to do exactly the same thing to the entire left side and the entire right side of this equation. So that's what I'm going to do here. I'm going to take the left side of the equation, 1 over 2 minus y times y prime, and I'm going to integrate that with respect to x. Now the next thing that I'm going to do is I'm going to have a look at this quantity right here, y prime dx. If I remember that y prime is the same thing as dy over dx, and I hit that with another copy of dx, then these two dx's essentially cancel each other out. And I'm left with just dy there from that product. And that's step number 3, rewrite y prime dx as dy on the left side. When I do that, I have on the left side an integral of a function of y with respect to y, and an integral of a function of x with respect to x. And this is how it should work out every single time if you have done the work correctly up to this point. You should, if correct, so far, the left integral should contain no x's, and the right integral should contain no y's. If you have a mixing or a mismatch in your equation where you have both x's and y's on one side of the equation, if you have a mixing of x's and y's, you have done something wrong at this point. By the time you reach step 3, the x's and y's should be completely separated from each other. An integral of a function of y with respect to y on the left, separate from an integral of x with respect to x on the right. If those are not separated, you've made a mistake, or the differential equation was not actually separable in the first place. Okay, so if you have truly been able to separate the y's from the x's, and if you are left with an equation that looks like this one, only y's on the left and only x's on the right, then at this point you can just calculate the integrals on the left side and on the right side separately. And that's step number 4. Calculate the integrals on the left and right, remembering to include a plus c, a plus constant, on at least the right side. So in the context of our running example, the left integral is the integral of 1 over 2 minus y dy. And this is something that I could integrate, for example, using a u substitution. For example, I could let u be equal to this denominator so that du was equal to negative dy. So with that substitution, I'm now integrating negative 1 over u du, which gives me negative natural log of u. And if I put back the original expression for u, I would get negative natural log of absolute value of 2 minus y. And if I integrate the right side is just the integral of x, so that's really straightforward. That would just be equal to 1/2 x squared, and the right side integral is where I would include the plus c. Now that I have evaluated both integrals, I can say, okay, the left-hand side, negative natural log, should be equal to the right-hand side, 1 over 2 x squared plus c. And this would be the conclusion of step number 4, where I have integrated the left side and the right side of the equation, including a plus c on the right. Now that I've completed the integral, this is not a differential equation anymore, is it? This is just an equation containing x and y. So in this situation, now if I want to finish finding y, all I have to do is solve this equation algebraically. So this is where you learn, you deploy all the different techniques that you learned in algebra to try and extract y from this mess. For example, I'll apply a minus sign to get rid of this minus in front of the natural log. And I can apply an exponential to both sides to get rid of this natural log. I can apply a plus minus to get rid of the absolute value. And then all that's left for me to do is just rearrange some terms to solve for y. So I get 2 either added or subtracting an exponential to the power negative 1/2 x squared minus c. This right here is the description of the format of all the functions that make my original equation true. If you're trying to find all the functions that satisfy y prime plus x times y equals 2 times x, all those functions look like this. 2 and either add or subtract an exponential raised to the power negative 1/2 x squared minus a constant. Okay, so this is the process of solving differential equations that are separable. Start by separating the x's and the y's, then integrate both sides. And what you should wind up with is an integral on the left with respect to y and an integral on the right with respect to x. Calculate both of those integrals and then solve the result algebraically for y, and that should do it. With our remaining time, let me go ahead and show you a few more examples of this process. So, for example, we checked earlier that this equation y prime equals x times y is separable. So let's use the 5-step technique that we introduced a little while ago to solve this equation. So I will start by rewriting the equation with y and x separated in the standard format, and then I will integrate both sides of the equation with respect to x. Now on the left-hand side, this y prime dx becomes dy after simplification. And so on the left side, I have an integral containing only y's, and on the right side, I have an integral containing only x's. I integrate the expression on the left, and I get natural log absolute value of y. I integrate the expression on the right, I get 1/2 x squared plus c, including the c in the right integral. And then all that I have left to do is go back to my algebra days and solve this for y algebraically. So I will use a natural exponential to get rid of the natural log. And then I will use plus minus to get rid of absolute value. And this would be the description of all the functions y who have this property, that if you take the derivative of this function, what you will get is a single copy of x more than what you had originally. Let's do it again on this additional example that we saw of a separable differential equation, y prime equals 3y plus 2. First, I'm going to rewrite this in the format function containing only y's times y prime equals function containing no y's, in this case, just the constant function 1. And I'll integrate both sides of this equation with respect to x. And I will simplify y prime dx to dy. And then sure enough, what I have here is an equation on the left, an integral which contains only y's, and on the right, an integral which contains only x's. I can integrate this expression on the left using a u substitution. And this integral on the right-hand side is very straightforward. The left side will give me the integral of 1/3 times 1 over u du, which becomes 1/3 natural log of u, which is equivalent to 1/3 natural log 3y plus 2. The right side is just going to be x, and here I include the plus c. And so setting those equal to each other, I have 1/3 natural log absolute value of 3y plus 2 equals x plus c, and all I have to do at this point is solve this algebraically for y. So I multiply by a 3 to cancel the 1/3. I use an exponential to get rid of the natural log. I subtract that 2, and then I divide by that 3. So what we're saying is that this is the format of all the functions that make this equation true. This is the format of all the functions that make this equation true. The format of all those functions is e to the 3x plus 3c minus 2 all over 3. And one final example. Here we have the last separable equation that we identified earlier. Y prime e to the negative y equals e to the x was the rewrite of this equation in the standard format. Integrate both sides with respect to x, doing the exact same thing to both sides. Rewrite that integral on the left, rewrite y prime dx as dy. Complete both integrals, including a plus c on the right side, and then algebraically solve for y. Using a natural log to get rid of the exponential, and then applying a minus sign to get rid of that negative on y. This would be the description of all the functions that make this equation true. If you want y prime to be the same thing as e to the x plus y, the functions that you would need to do that job are of this format: negative natural log of negative e to the x minus some constant.